Now we will continue our review of the basic math in order to do some calculations in mechanics. So last time we have introduced the derivative. The derivative was defined as the limit as delta x goes to 0, y of x plus delta x minus y of x over delta x. It's the slope of the curve at the point at which we are taking this derivative. Now, some important properties of the derivatives we should be aware of. If we're trying to calculate the derivative of a product, the derivative of g times h is g times derivative of h plus h times derivative of g. This is assuming that g and h are functions of the variable x. Another important property is if we're taking the derivative of a sum of two functions of x, it's the derivative of the first function plus the derivative of the second function. If we have a function of x, y is a function of x, but at the same time x is a function of z, it's g of z. And if we're trying to find the derivative of y with respect to z, we have to take the derivative of y with respect to x first, and then we take the derivative of x with respect to z. So this is known as the chain rule. Second derivative of y with respect to x means we're taking the derivative of the derivative. So if we have the derivative of y with respect to x, we take its derivative with respect to x again. That's the second derivative. If we're taking the derivative of the ratio of two functions, g of x over h of x with respect to x, it is the function at the bottom, h multiplied by the derivative of the function on top, dg dx, minus the function on top multiplied with the derivative of the function at the bottom, dh dx, divided by the function at the bottom squared, h squared. Okay, so let's look at a quick example. Y of x is x cubed over x plus 1 parentheses squared. There are two ways I can look at this. It is x cubed times x plus 1 to the power minus 2. So I can say that this is the product of two functions, f of x and g of x. Therefore, I can use the first one. So I take the derivative of the x cubed with respect to x multiplied by x plus 1 to the power minus 2, and then I leave x cubed alone and I take the derivative of x plus 1 with respect to x plus 1 to the power minus 2. So this gives me derivative of x cubed with respect to x is 3x squared multiplied by x plus 1 to the power minus 2, that's x plus 1 to the power 2 in the denominator. And then I have x cubed times derivative of x plus 1 to the power minus 2, that is minus 2 x plus 1 to the power minus 3, which is minus 2 over x plus 1 parentheses cube times x cubed. Now you can see that in the first term I have x plus 1 square, in the second term I have x plus 1 cube in the denominator. So I multiply the first term with x plus 1. 3x squared x plus 1 minus 2x cubed divided by x plus 1 cubed, the common denominator now. So that gives me 3x cubed minus 2x cubed, which is x cubed, and plus 3x squared divided by x plus 1 cubed. So that's the answer. Alternatively, I can use this rule, the ratio of the two functions. First, I take the derivative of the top, d dx x cubed, multiplied by the bottom, x plus 1 squared, minus, then I leave the top alone and take the derivative of the bottom with respect to x, and divided by the bottom squared, x plus 1 to the power fourth, to the fourth power. So this would be x plus 1 squared times 3x squared minus 2x cubed x plus 1. So too many x plus 1s, one of the x plus 1s disappear, and I find that I have 3x squared x plus 1 minus 2x cubed over x plus 1 cube, which is exactly the same result I obtained using the property of the product of two functions. So they give the same result. Okay, now let's look at another example. Find the derivative of 1 over x using the definition of the derivative. Okay, so the derivative of 1 over x with respect to x is, by definition of the derivative, the limit delta x goes to 0, f of x plus delta x, which is 1 over x plus delta x, minus f of x, 1 over x, divided by delta x. This is the limit delta x goes to 0. Now, I multiply the first term with x, the second term with x plus delta x, so I obtain x minus x plus delta x divided by x plus delta x, common denominator, and then I have another delta x. So this gives me the limit as delta x goes to 0, because plus x and minus x will cancel. I will be left with a minus delta x on top. Divided by x plus delta x. Delta x's will cancel since delta x is finite. Therefore, I have minus 1 over x times x plus delta x. If I set delta x equals to 0 at the bottom, I obtain minus 1 over x squared, which is the derivative of 1 over x with respect to x. Okay, now an important series expansion that we use very frequently is called the Taylor series expansion. Basically, this is used to find an approximate expression for the behavior of a function in the neighborhood of a specific point. Okay, so we want to know, well, we have this general function here, but we want to know, for example, the behavior in the vicinity of this point. So is this linear here, or is it more like x squared or x cubed? So how is this function behaving in the vicinity of this point? So that's the question. So the Taylor series expansion is basically the first term. We evaluate the function at that point. So we're trying to find the behavior of the function at x equals x0. So first we evaluate it. Then we take the derivative with respect to x, evaluated at x0, divided by 1 factorial, which is 1, multiplied by x minus x0. Then we take the second derivative, evaluated at x0, divided by 2 factorial, x minus x0, parentheses squared. Then we take the third derivative, evaluated at x0, divided by 3 factorial, x minus x0 cubed, etc. So this is how the Taylor series expansion goes. Now if we apply this to the function 1 plus x to the power n, and we're trying to find its behavior in the vicinity of x equals 0. So x is much less than 1. So first we evaluate it at x equals 0, we get 1 to the power n. Then we take the derivative, it is n times 1 plus x to the power n minus 1, evaluated at 0, becomes n times 1 plus 0 to the power n minus 1 over 1 factorial, x minus x0, so it's x minus 0. And then we take the second derivative, n minus 1, 1 plus x to the power n minus 2, evaluated at x equals 0, divided by 2 factorial, x minus 0 squared, etc. So we obtain 1 to the power n is 1, and 1 plus 0 to the power n minus 1 is 1, so it is n divided by 1 factorial, which is n, so we have x minus 0x, 1 plus nx, and then we have n minus 1 over 2 factorial, x squared, etc. So that's the behavior for x much less than 1. Now, another example is exponential that we commonly use. Evaluated at 0, we have e to the 0 plus derivative is e to the x, derivative is itself, divided by 1 factorial x minus 0. So we obtain 1 plus x, and the second derivative is again itself, evaluated at 0, e0, e to the power 0, which is 1 over 2 factorial x minus 0 squared, x squared. So we obtain 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And for the sine function, what is the behavior for small x values? First we evaluate it at 0, sine 0 is 0. Then we take its derivative, it's cosine x. Cosine x evaluated at 0 is cosine 0, which is 1. 1 over 1 factorial is 1, x minus 0 is x. And then take the derivative of cosine with respect to x, we obtain minus sine, which is 0 when evaluated at 0. So we obtain x. Sine x behaves as x in the vicinity of x equals 0. For cosine, we have cosine 0. Cosine evaluated at 0 is 1. Take the derivative, we get minus sine x. Minus sine 0 is 0, so that doesn't give a contribution. Take the derivative of minus sine x with respect to x, we obtain minus cosine x. So it is minus cosine 0 divided by 2 factorial, which is minus 1 over 2, x minus 0 square, which is x squared. So this behaves as 1 minus x squared over 2, etc. So these are some important results we will be using very frequently. 1 plus x to the n behaves as 1 plus nx. E to the x behaves as 1 plus x squared over 2 factorial, etc. The first three terms, non-zero terms. Sine x is behaves as x, and cosine x behaves as 1 minus x squared over 2. So sometimes we need to go to higher order terms, but this is basically the procedure that we follow to find the Taylor series expansion. Now, as for the integral calculus, we can consider integration as anti-differentiation. It's inverse of differentiation. So the integral sign is like an S here. Then we have f of x, which is the integrand multiplied by dx. So that gives us an indefinite integral. However, if you look at this function as f of x as a function of x, in the interval x1 to x2, and if we pick a x value in this range, xi, and we pick a delta xi, a very small infinitesimal distance on the x-axis, the area under this curve is basically, because this value, let me put here the value. So this is going to be f of xi. So f of xi times delta xi is basically the area of this rectangle. So if I add all of these areas, in the limit delta xi goes to 0, sum over I f of xi delta xi, that's called the Riemann sum, and we find the integral x1 to x2 f of x dx, which is called a definite integral. So it means we're calculating the area under the curve f of x in the interval x1 to x2. So here's an example. Integral of x to the n dx. It is x to the n plus 1 divided by n plus 1 plus a constant. Why? Because x to the n plus 1 has a derivative n plus 1 times x to the n. N plus 1s will cancel. We will obtain x to the n. We need to add a constant here. Constant. Why? Because the derivative of a constant is always equal to 0. So we can add a constant. And this is going to be true when n is not equal to minus 1. Why? N equals to minus 1 is 1 over x, and 1 over x is the derivative of natural logarithm of x. So that would be not correct for n equals minus 1. If we take a definite integral in the interval x1 to x2, then basically we evaluate this integral x to the n plus 1 over n plus 1 in the interval x1 to x2. So first we put x2 here, x2 to n plus 1 minus, then we put x1 to n plus 1 divided by n plus 1. So, for example, if we're taking the derivative of the integral of x to the 3 over 2 dx in the interval 0 to b, this would be x to the 3 over 2 plus 1 divided by 3 over 2 plus 1, 0 to b. So that would be x to the 5 over 2 divided by 5 over 2, which is 2 over 5, b to the 5 over 2, because when evaluated at 0, it would give us a 0. Now, an important trick that we use in taking the integrals is called partial integration or integration by parts. And this is based on the product of the derivative of the product of two functions. D of uv is equal to u dv plus v du. So that was the first property that we have seen. If I take the integral of this equation, integral of the derivative uv is integral u dv plus integral v du. Because the integral of duv, anti-differentiation of differentiation, gives me the function uv, it is uv equals integral u dv plus integral v du, or integral u dv can be written as the product of the functions uv minus integral v du. So this is what we use to calculate the integral. For example, if we're trying to calculate the indefinite integral of x squared e to the x dx. Now, if you recognize x squared to be function u, e to the x dx as function, the derivative dv, differential of the function v, dv, then you see that if you take the derivative of x squared with respect to x, you will have 2x, so du is 2x dx, and the integral of e to the x dx gives us the function v, which is e to the x. So we have uv, which is x squared e to the x, minus integral v du, which is minus integral e to the x 2x dx. So that's what we have. But we're not done, because we have to take the integral of x e to the x as well. So for that, we set u is equal to x, du is dx, dv is e to the x dx, v is e to the x. So that gives us uv, which is x e to the x, minus integral v du e to the x dx. The integral of e to the x dx is e to the x, and if we use the minus 2 here, so we're going to have x squared e to the x minus 2x e to the x, and here we're going to have plus 2 e to the x, of course. And so if we put this in e to the x parentheses, we have x squared minus 2x plus 2. There's a mistake here. So this will be plus 2. So the answer for this integral is e to the x, x squared minus 2x plus 2. And I'm going to put another arbitrary constant here. Why? Because this is an indefinite integral, and the derivative of a constant is always equal to 0. So this was a minus sign. X squared minus 2x plus 2. Okay, so in my final answer, I have e to the x, x squared minus 2x plus 2, plus a constant, arbitrary constant, whose derivative will give me a 0 here. So let me make sure that I have done this correctly. So for the integral x e to the x, I used x e to the x minus integral v du, which is e to the x dx, and that gave me a minus e to the x. So minus minus becomes a plus, so I will have minus 2x e to the x and plus 2e to the x. That looks correct. So this is going to be my final answer. Okay, so in summary, we have finished our math review here. We talked about the derivative of a function, which is the slope of the function at the point of interest. It is the limit as delta x goes to 0, f of x plus delta x minus f of x over delta x. We need to know the common derivatives of functions that we use very frequently. The list was given here. Some properties of the derivatives: derivative of the product of two functions, sum of two functions. What if a function is a function of a variable where the variable is also a function of another variable? Then we have the chain rule, the definition of second derivative, and the derivative of the ratio of two functions. The Taylor series expansion is something we use very frequently to find the behavior of a function in the neighborhood of a specific point. So we talked about how to calculate the behavior in the vicinity of a point. And some important Taylor series expansions for x equals 0 were considered. We have to know these by heart. And as for the integral, we have two types of integrals, indefinite and definite. If the integral has limits x1, x2, then that means we're calculating the area under the curve f of x in this interval, which is found by evaluating the Riemann sum in the limit delta x goes to 0. The derivative, the integral can be considered as antiderivative, so anti-differentiation is integration. And when we take an indefinite integral, we have to be careful about adding an arbitrary constant because the derivative of a constant is 0. And then we talked about an important technique of integration that's called integration by parts or partial integration, which is based on the derivative of the product of two functions. duv is u dv plus v du.